Welcome back.
Hey.
Alie Astrocyte here. Are you ready for some action? No, not like that. I meant action potentials. Get your head out of the gutter.
Yes.
Last week, I explained how the different concentrations of ions create the resting potential of the neuron, with a more negative charge on the inside of the cell. If you missed that episode or need a refresher, check it out here. Now let's talk about how that resting potential turns into a signal, the action potential. Resting potential is a very careful balance. A lot of things have to be working together to maintain the proper voltage. When you tip the balance, the whole thing collapses, like a Jenga tower. So, say you have the signal come in from another neuron, telling your neuron that it has to pass the message along. This signal means that you have some unexpected positive ions bumping around with your negative ions at the membrane. The voltage starts to creep up, going from about negative 70 millivolts to negative 55 millivolts. And, like a light bulb switching on, suddenly the entire balance has shifted. This threshold voltage causes new channels to open in the cell membrane, called gated ion channels. These channels are normally kept closed and only open when the voltage crosses a certain value. Essentially, it's like throwing open a floodgate. Kind of like that scene from Inception, you know, where Leonardo DiCaprio is standing in the dream and it's like whoosh, 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 right? Once the channels are open, positive sodium ions rush into the cell, causing a spike in the electrical potential. So the inside of the cell becomes more positively charged than the outside. This is called depolarization, when the cell ditches its normal negative inside, positive outside configuration. This signal moves down the length of the cell from end to end as the positive sodium ions further up the membrane bump downstream channels into opening. Think of the crowd in a baseball stadium starting to do the wave. You don't stand up and throw your arms in the air until the people sitting next to you do it first, because you have to wait for the signal to reach you, or else the whole thing falls apart. That's how the signal moves in your cell. It has to go in a specific order and direction, or else the whole process will get messed up. Neurons are very good at their job. By opening all of the sodium channels, the electrical signal gets passed down the line to the next cell, and the neuron's job is done. For now. However, the cell has allowed almost the maximum amount of sodium into the cell that it possibly can, so the inside of the cell membrane is very positively charged. Just like a dead battery, all of the ions have been used up and crossed the membrane, so there's nowhere else for the potential difference to go but down. This same positive charge actually starts to shut off those gated ion channels, closing them almost as quickly as they open in the first place. As these channels close, your cell goes to work pumping the excess sodium back out, using ion pumps in the membrane. The potential difference of the membrane starts to drop very rapidly, returning to normal. But wait, did you see that? What about that little dip at the bottom, where the potential has actually gone below the resting value? When the action potential fires, the potassium balance changes too, as extra potassium channels open. That's how you get this dip. The cell hyperpolarizes, actually reaching an electrical difference even more negative than normal. Over time, the membrane adjusts itself, and the ion channels and pumps return everything to their normal resting state, and you get back to your normal resting membrane potential. This whole process, from the first inklings of positive charge inside the cell to the hyperpolarization after the action potential has been fired, can take less than a millisecond. 1/1000th of a second is all the time it takes for your cell to process this information and adjust its channels and pumps accordingly. This is how your body is able to send signals so quickly from place to place.
Hang on a sec.
You say,
I still don't quite understand this action potential thing.
well, my friend, as it turns out, biophysics are pretty complicated. But don't fret. If you have more questions about the mechanics of the action potential, please check out these resources.
Okay.
You're saying to yourself,
I get how this membrane potential thing works and how it sends a signal in a single cell. But how does that signal get to the next cell down the line? Does the neuron use ions for that too?
and to answer that question, you're gonna have to wait until the next episode. If you liked what you learned, give this video a thumbs up and subscribe to become a brainiac. Then tune in next week to learn about the synapse. I'm Alie Astrocyte, and until our next transmission, over and out.